Picture this. You are standing in an open field. The sky is bright. Birds are making noise. The sun is exactly where it has always been. Then, something enormous begins racing toward you. Not a storm, not a wall of rain, a shadow. The moon's shadow. It moves across the ground, swallows the landscape, and turns day into night. For a few incredible minutes, the sun disappears. Then the shadow moves on. But what if you moved with it? Could you climb into a car, press the accelerator, and keep the eclipse going? Could a plane chase it? Could you somehow turn 2 minutes of darkness into an entire afternoon? In other words, could you outrun a solar eclipse? First, we need to clear up something important. A solar eclipse is not the sun switching off. The sun is doing exactly what it normally does. The moon simply passes between the sun and Earth and casts a shadow onto our planet. That shadow has two main parts. The large, lighter outer shadow is called the penumbra. If you stand inside it, the moon covers only part of the sun. That creates a partial eclipse, but at the center is a much smaller, darker shadow called the umbra. If that passes over you, the moon completely blocks the bright face of the sun. That is totality. And totality is the part everyone wants. The sky darkens, the temperature can drop, stars and planets may become visible, and the sun's faint outer atmosphere, the corona, appears around the moon. The problem is that the umbra is surprisingly small. Compared with the size of Earth, it is more like a narrow spotlight than a continent-sized blanket. As Earth rotates and the moon continues along its orbit, that spotlight sweeps rapidly across the planet. NASA explains that the full shadow crosses Earth over several hours, but any one location usually experiences totality for only a few minutes. So if you want the eclipse to last longer, you have to move with the shadow. Let's begin with the least promising option. Running. Imagine the edge of totality approaches from behind you. The landscape goes dark. You sprint forward. For a moment, this feels heroic. You are racing the moon. Unfortunately, the moon does not seem impressed. An eclipse shadow can move across the ground at well over 1,000 miles per hour, with the exact speed changing depending on the eclipse and where the shadow lands on Earth. That is slightly faster than the average person by approximately 1,000 miles per hour. Even the fastest human sprinter would lose almost immediately. The shadow would pass over, totality would end, and you would be left jogging in daylight while wearing eclipse glasses. So running is out. What about a car? Now we are at least using an engine. Suppose you position yourself on a perfectly straight highway that follows the exact path of the moon's shadow. No traffic, no turns, no construction, no police officer asking why you are doing 120 miles per hour while staring at the sky. Could you stay inside totality? Not for long. Even on a fast highway, the shadow is usually moving many times faster than your car. You might gain a few extra seconds if you begin near the front edge of the umbra and drive in exactly the correct direction. But you would not be chasing the eclipse. You would be watching it disappear into the distance. A car is useful for driving from one viewing location to another before the eclipse begins. Once totality arrives though, the race is essentially over. At this point, the eclipse shadow might seem strangely overpowered. The moon itself moves around Earth at roughly 1 kilometer per second, but the shadow on Earth is not a physical object traveling along the ground. It is a moving point where the sun, moon, and Earth line up. Think of shining a flashlight at a distant wall. Move your wrist slightly, and the bright spot can sweep across the wall much faster than your hand is moving. Nothing on the wall is actually traveling at that speed. The location of the light is changing. The moon's shadow works in a similar way. Its speed across the surface depends on several moving pieces. The moon's orbit, Earth's rotation, the angle at which the shadow strikes the curved planet, and where you are along the eclipse path. Near the middle of some eclipse paths, Earth's rotation helps carry the ground in roughly the same direction as the shadow, reducing its apparent speed. Near sunrise or sunset, the shadow may strike Earth at a shallow angle and race across the surface much faster. So there is no single universal eclipse speed. The moon's shadow is fast, but also annoyingly inconsistent. How about an airplane? Now we are getting somewhere. A passenger jet can travel around 500 to 600 miles per hour. That still may be much slower than the shadow. But unlike a car, a plane can follow a carefully calculated route without worrying about roads, mountains, or someone merging without signaling. A plane also has another major advantage. It flies above much of the weather. That matters because clouds have ruined many carefully planned eclipse trips. Imagine traveling across the world to see a total eclipse, only to experience a very accurate simulation of looking at a gray ceiling. By flying in the same direction as the moon's shadow, an aircraft can extend totality. It does not have to match the shadow's speed perfectly. It simply has to reduce the speed at which the shadow passes over the observers. If the umbra is moving east at 1,500 miles per hour, and your plane is moving east at 500, the shadow is now passing you at a relative speed of about 1,000 miles per hour instead. You still lose, just more slowly. That can turn several minutes of totality into several additional minutes. In 2010, for example, an Eclipse chasing passenger flight remained in totality for more than 9 minutes, substantially longer than observers at a fixed point on the ground. That is impressive, but we can do better. On June 30th, 1973, scientists attempted something extraordinary. They used Concorde 001, an experimental supersonic aircraft, to chase a total solar eclipse across North Africa. Concorde flew at more than twice the speed of sound. The route had to be calculated with extraordinary precision. If the plane arrived slightly early, slightly late, or too far to one side, it would miss the narrow umbral shadow. Instead, Concorde intercepted it, then flew along with it. The result was astonishing. The scientists aboard experienced approximately 74 minutes of totality. Not 4 minutes, not 10, 74. The aircraft effectively stretched one of nature's briefest spectacles into a mobile astronomical laboratory. So yes, humans have successfully chased a solar eclipse for more than an hour. But did Concorde actually outrun it? Not quite. It matched the shadow closely enough to remain inside it for much longer than anyone standing on Earth could. That is less like outrunning the eclipse, and more like convincing it to let you come along. Now let's take the idea to its logical and slightly ridiculous conclusion. What if you had the perfect aircraft? Unlimited fuel, no mechanical problems, no international borders, no passengers asking when the beverage cart is coming back? Could you follow the shadow forever? No. Even if your vehicle could perfectly match its speed, the shadow does not remain on Earth forever. It enters the planet at sunrise, sweeps across the surface, then leaves at sunset. The geometry changes continuously as the moon moves, Earth rotates, and the curved surface falls away from the shadow. Eventually, the umbra slides off Earth and continues into space. To keep following it, your aircraft would have to leave the atmosphere, and then leave Earth. At that point, you are no longer chasing an eclipse. You are chasing the moon's shadow through space, which is a very different travel package. On August 12th, 2026, a total solar eclipse will cross parts of northern Russia, Greenland, Iceland, the Atlantic, Spain, and a small area of Portugal. Many other regions will see a partial eclipse. For most locations within the path of totality, the sun will be completely covered for less than 2 minutes. Near the center of the path, totality will last slightly longer, but still under 2.5 minutes. That makes it a perfect reminder of just how brief these events are. You may wait years, travel thousands of miles, check the weather every 12 seconds, then the sky goes dark. And before your brain fully processes what is happening, the sun returns. Could an aircraft extend the experience? Yes. With the correct flight path, timing, permissions, weather conditions, and a rather enthusiastic budget. Could your rental car do it? Probably not, especially if you decline the optional insurance. So, could you outrun a solar eclipse? On foot? Absolutely not. In a car? No. In a normal passenger aircraft? You could chase it and gain some time. In a supersonic jet? Now you have a real chance of staying inside the shadow for much longer, but even the perfect vehicle cannot keep the eclipse on Earth forever. The moon's shadow is not a thing you can catch. It is a temporary alignment, a moving intersection between three worlds: the sun, the moon, and Earth. For a few minutes, everything lines up perfectly. Then the geometry changes, and the darkness moves on. Maybe that is part of what makes a total eclipse feel so extraordinary. You cannot pause it. You cannot ask it to wait. You can prepare for years. But when the shadow arrives, all you can really do is look up. Safely. With proper eclipse glasses before and after totality. and enjoy the brief moment when the moon wins a race against nearly everyone on Earth. Nearly. Because in 1973, Concorde came surprisingly close.